Welcome to the Joy of Architecture. Today we're diving into a stack of sources you've sent our way, all about something called Server Sent Events, or SSE. Think of this as your shortcut to understanding one of the quiet workhorses behind the real-time web doc, those moments when a website updates you, instead of you having to constantly hit refresh. Our mission is to unpack what SSE is, why it exists, how it works under the hood, and where it fits in the complex landscape of modern web communication.
Exactly. We'll trace the path from the early days of the web trying to, simulate real time through the technical details of SSE itself and explore where it excels and where you might need different tools. It's really about seeing the specific problem SSE was built to solve and how it fits into the broader story of dynamic web applications.
All right, let's unpack this by starting at the beginning, the historical problem. The web, for a long time, was a simple request-response model. You type a URL, your browser asks the server for a page, the server sends it back. Done. What happens when the server has something new for you and you haven't asked for anything?
That's the core problem space, really, that drove the need for server-initiated updates. As web applications moved from static documents to dynamic experiences, think chat rooms, live sports scores, stock tickers, social media feeds, users started expecting information instantly, without having to manually refresh the page. The old request-response model just couldn't keep up with this shift in user expectations.
And the initial attempts to solve this felt a bit like clever workarounds, right? Like just asking the server over and over again.
Precisely. The earliest common technique was short polling. Your browser would send a request, the server would respond immediately, often with nothing new, and then after a short delay, the browser would just ask again and again every few seconds.
That sounds incredibly chatty and, well, inefficient for the server.
Oh, it was. High server load because of all those frequent requests, even when there was no new data. Lots of wasted network traffic sending back empty responses. And updates were delayed until the next scheduled poll, so latency was high. The source notes highlight that inefficiency.
Okay, so people quickly realized that wasn't great. What was the next evolution? Long polling.
Yeah, that led to long polling, sometimes also grouped under the umbrella term COMET. Here, the client still sends an HTTP request, but the server holds the connection open. It doesn't respond until there's actual data available or maybe a predefined timeout occurs. Once data is sent, the server closes the connection and the client immediately initiates a new long polling request.
Ah, okay, so you reduce the empty responses and get updates sooner when data is ready. The source mentioned lower latency compared to short polling.
Right. Better latency, less wasted bandwidth on empty polls. Definitely an improvement for receiving data.
But what were the downsides there? It sounds like it shifts the burden.
It absolutely did. Maintaining potentially thousands or, millions of open connections waiting for data is resource intensive for the server. Consumes memory, ties up connection handling resources. The source notes high memory for open connections. Plus, managing the connection lifecycle of the server closing, the client immediately reopening adds, moderate to complex logic on both sides. And every single message still carried the full weight of HTTP headers. Not ideal for frequent small updates. And on top of that, network intermediaries like proxies often weren't built for these long-lived hanging connections and could interfere.
Got it. So polling techniques were workarounds with significant trade-offs, driven by this increasing need for real-time updates in Web 2.0 applications. What other methods were being explored around that time? Anything before polling, even?
Well, even earlier, things like Java applets or Flash could open raw sockets, but they required browser plugins, which wasn't ideal. Then, with the rise of AJAX, developers started experimenting with techniques like XML HTTP request streaming, or XHR streaming. This was around the early 2000s. It became a key part of those COMET strategies popularized a bit later.
XHR streaming. That sounds like it's getting closer to SSE. How did that differ from long polling?
Well, instead of the server closing the connection after sending data with XHR streaming, the server would send the initial response headers, but then keep the connection open. And it would continuously stream data in chunks within the response body. The client-side JavaScript using XML HTTP requests would have to listen for ready state equals 3, meaning data is loading, and incrementally parse the response text property as new data arrived.
Wow, okay. So you were essentially building your own streaming parser and connection manager in JavaScript. That sounds fragile.
Exactly. It was innovative for sure, but manual parsing was complex and definitely error-prone. Handling potential network interruptions, browser differences, and how they expose the streaming data, managing reconnects, it all required custom, often fragile code. The source even notes browser inconsistencies were a big problem. Powerful maybe, but Felt like a hack built on top of a request response API.
That sounds like a really strong case for standardization. Was that the driving force that led to WebSockets and SSE around the late 2000s, early 2010s?
Absolutely. The need for standardized, efficient, real-time communication methods was clear. WebSockets, standardized in RFC 6455 back in 2011, offered a pretty radical shift. A full duplex, bidirectional channel over a single TCP connection, established via an initial HTTP handshake. Really ideal for interactive scenarios like chat apps, online gaming, collaborative tools, anywhere the client and server need to send messages freely back and forth.
Okay, so full two-way communication and SSE. Where did that fit in alongside WebSockets?
SSE, standardized as part of the WhatWG HTML5 specification, which is now the HTML Living Standard, it took a different path. Instead of building a whole new protocol, it basically formalized and standardized that XHR streaming pattern, but directly on top of HTTP. Its design goal was simpler, strictly unidirectional server-to-client push.
Oh, okay.
The source confirms it was standardized by the WhatWG and built on earlier browser experiments, like Opera even had an experimental server-sent DOM events thing way back in 2006.
That's a fun bit of history. So SSE basically took the XHR streaming idea but made it a proper first-class citizen in the browser?
Precisely. It standardized the format, gave us a dedicated browser-native event source API, and crucially included built-in features, especially for reliability, that you had to code yourself with XHR streaming. The broad adoption across all the dominant browser engines really cemented SSE status as a standard web technology. We're talking Safari 5 plus Beg, Chrome 6 plus Analegs, Firefox 6 plus Edge, Opera 11 plus Edge, 79 plus Beg. It even pops up in formal IETF documents like RFC 8895 for ALDO incremental updates, which shows its acceptance beyond just browser APIs.
Okay, fascinating journey from pulling hacks to a standardized API. So conceptually, what exactly is server-sent events today? Can you break it down?
At its core, SSE is a mechanism for a server to send updates to a client over a single, persistent HTTP connection. That connection is established after the client makes an initial request. The absolute key thing is that it's strictly one-way, server to client. The client cannot send data back over that same connection.
And this unidirectional nature is the defining characteristic compared to WebSockets, right?
Absolutely. It's the fundamental difference. If your application primarily needs the server to notify the client of new information, without the client needing to send frequent messages back on that same channel, SSE's simplicity for that one-way flow is a major advantage. It simplifies things.
Where would you actually use this in practice? What are the classic use cases where SSE is a really good fit?
Oh, think of scenarios where a server has real-time information that multiple clients just need to display. The source lists some great examples, things like notifications and alerts, social media pings, system alerts, live dashboards and monitoring, displaying real-time analytics, server metrics, maybe IoT data coming in.
Right.
Streaming data feeds are another big one. News headlines, stock tickers, sports scores. Also progress updates, like showing the status of a long-running background task on the server. Even streaming logs to a web UI, or live responses from AI models like text output from a chatbot.
Those are super common. So if I just need to push updates to the user, SSE sounds like a strong candidate. But how does it stack up against the alternatives? Let's quickly revisit those comparisons. WebSockets first.
Okay. WebSockets. Bidirectional, full duplex, SSE. Unidirectional server to client only. WebSockets use a custom WebSocket protocol, WSDAT or WOS over TCP. SSE just uses standard HTTP or HTTPS. WebSockets can handle both text and binary data. SSE is text only, specifically UTF-8. And importantly, SSE has built-in automatic reconnection and event ID tracking handled by the native browser API. That simplifies client-side code quite a bit compared to WebSockets, where you often have to implement that logic yourself.
So WebSockets for chat, gaming, collab tools, SSE for feeds, notifications, dashboards. Got it. What about HTTP2 server push?
Totally different purpose. That's an optimization for initial page load. Pushing static assets like CSS or JavaScript, the server thinks you'll need immediately, not for streaming application events like SSE does.
Okay, clear distinction. GraphQL subscriptions.
Right, that's a higher level pattern within the GraphQL world. It uses an underlying transport protocol, which could be WebSockets, or yes, it could be SSE, to deliver real-time updates for specific GraphQL queries.
Ah, so SSE could actually be the engine behind GraphQL subscriptions sometimes.
Exactly. You might choose SSE as the transport for its simplicity, or maybe better firewall traversal since it's just HTTP.
Interesting. Last one, MQTT. Hear that a lot with IoT.
Yeah, MQTT is a lightweight publish-subscribe protocol, really designed for IoT device communication, constrained devices, low bandwidth networks. It's bidirectional, handles binary data, has quality of service levels built in, and requires an MQTT broker in the middle. SSE, again, is unidirectional text-only, no built-in QoS beyond TCP and event IDs, and no built-in broker concept.
So for displaying IoT data in a web browser.
SSE is often the bridge to the browser. The devices might talk MQTT to a central server, and then that server uses SSE to push the data out to web dashboards for users to see. SSE is simpler and more browser native for that display layer.
Okay, that really clarifies where SSE fits. Its design philosophy seems to be all about simplicity, leveraging standard HTTP, reliable unidirectional push, and those built-in reliability bits for the client.
That nails it. It addresses the polling limitations without the complexity of bidirectional protocols when you just don't need them.
Let's get a bit more into the plumbing then. How does this text event stream protocol actually work over HTTP?
Okay, so it starts with a standard HTTP GET request from the client to some endpoint on the server. The server responds with 200 OK, but crucially includes the header content type text event stream. The source calls this critical. This header is the signal to the browser's event source API to treat the response differently as a stream. Other headers like cache control, no cache, and connection keep alive are usually important too. But the really big difference is the server keeps the underlying TCP connection open after sending those initial headers. It doesn't just send the response and close like a normal HTTP request.
So the server keeps writing data into this open connection. What does that data actually look like? Is it JSON?
Nope, it's simpler than that. It's a stream of plain UTF-8 text. Individual messages or events are separated by a double new line, so N. Each message itself can contain several lines, and each line starts with a specific field name followed by a colon.
Like the data.field, that's the payload, right?
Exactly. Data holds the actual message payload.
Right.
A neat feature is if you have multiple data lines right after each other. They get concatenated into a single data value on the client side with new lines preserved between them.
Okay. What are the other important fields you might see?
Well, there's the event.field. This lets you name the type of event, like event.userUpdate. The client can then listen specifically for user update events using add-event-listener. If you don't include an event.field, it just defaults to a generic message event, which you'd catch with onMessage.
And ID, you mentioned that's key for reliability.
Absolutely crucial. The id field lets you assign a unique identifier to each event, maybe like id.msg123. The browser's event source API automatically keeps track of the ID of the last event it successfully received, the last event ID. Now, if the connection drops and the browser automatically reconnects, it sends this last event ID back to the server in a special HTTP header, last event ID.
Ah.
The server can then look at that ID and figure out, okay, the client saw up to message 123, maybe I need to resend a 124 onwards. This does mean the server needs to keep some history, a buffer of recently sent events, if it wants to support this recovery.
Makes sense. What about retry?
That's the server suggesting to the client how long, in milliseconds, it should wait before trying to reconnect after a connection drop. Like retry, 10,000 means wait 10 seconds. It lets the server influence the reconnection behavior, maybe to prevent clients hammering it immediately after a temporary glitch.
And what about lines that just start with a colon?
Those are comment lines. They're completely ignored by the client parser, but they're not useless. The source notes they're often used as keep-alive pings. Sending a comment line periodically keeps data flowing on the connection, which prevents network intermediaries or even the server itself from thinking the connection is idle and closing it prematurely.
So they're not just comments for humans, they're actually a functional part of keeping the stream alive. The whole format sounds pretty straightforward, especially since the browser handles the parsing.
Exactly. The simple text format is easy for servers to generate, and critically, the event source API in the browser does the heavy lifting. It parses the stream, fires the right events on message or named events, and handles the connection lifecycle, including that automatic reconnection. That's a huge plus. It simplifies the client-side code immensely.
How good is the browser support for this event source API these days? Is it everywhere?
Pretty much, yeah. It's natively supported in all modern web browsers. The source confirms this, listing wide adoption. Safari, Chrome, Firefox, Edge, Opera, basically everything except.
Let me guess. Internet Explorer.
You got it. Internet Explorer never natively supported SSE.
Of course not. Are there polyfills for older browsers, or is that just not a concern anymore?
Polyfills do exist.
Yeah.
Several event source polyfills have been developed that try to emulate the API, often using XHR streaming or long polling underneath. But honestly, the need for SSE polyfills is diminishing rapidly as I usage continues to drop. For most modern development, you can rely on native support.
Okay. What about limitations on the client side, particularly in browsers? Anything to watch out for?
The biggest historical limitation, and it was a big one, especially over HTTP one-on-one, is the HTTP one-down-one connection limits. Browsers typically limit the number of simultaneous persistent connections to a single domain. That limit is usually around 6. Since each SSE stream consumes one of those persistent connections, if you try to open, say, 7 SSE streams from the same web page to the same server,
The seventh one might just hang or block other requests?
exactly, or block images, CSS downloads, other API calls, it could become a major bottleneck if you needed multiple real-time streams on one page.
That sounds like a serious problem for complex apps. How was that resolved?
Well, for HTTP 1.1, it mostly wasn't. Browsers basically marked it as won't fix, encouraging migration to HTTP 2, and that's the key. HTTP 2 largely mitigates the strict connection limit problem. HTTP 2 allows multiplexing. You can have many logical streams running over a single underlying TCP connection, so you can have dozens, even 100 or more SSE streams multiplexed over that one connection, effectively bypassing the old HTTP 1.1 limit around 6.
Ah, okay. So using SSE over HTTP2 is almost essential if you plan on having more than just a few streams open simultaneously from the browser to the same origin.
Absolutely critical for scaling the number of connections from the client side. If you anticipate needing many streams, you need HTTP 2.
And quickly, what about mobile or IoT clients? Does SSE work there?
Yep, mobile web views in native apps support SSE just fine. A native mobile app could also implement an HTTP client to consume an SSE stream directly if needed, though often native push notifications are preferred for background updates. SSE is generally considered efficient for mobile use when the app is active, because it uses standard HTTP/HTTPS and benefits from compression. For IoT, like we touched on, SSE is usually for the data presentation or consumption layer, that web dashboard showing the data. It's generally not used for the actual device-to-server communication, where MQTT or CoAP are more common.
Okay, that makes sense. Let's shift focus to the server side then. How is the connection managed there? What does the server code need to do?
All right, so the server receives that initial HTTP GET request. It needs to send back the 200 OK response, but with those crucial headers: content type.text event stream, cache control.nocache, connection.keepalive. And then the core part. Instead of closing the connection, the server code must keep the underlying TCP connection open. This means the server needs to maintain some kind of list or collection of all active client connections, usually references to their response stream objects. It needs to know who to send events to. And critically, it needs to be able to detect client disconnections gracefully. When a user closes a tab or their network drops, the server needs to realize that connection is gone, so it can remove the client and release any associated resources like memory or file handles. Preventing resource leaks is vital when you have potentially many long-lived connections.
We mentioned the last event ID mechanism for recovery if the connection drops and the client reconnects. How does the server actually support that?
Right, so when the client reconnects, it might send that last event ID header. The server code needs to check for this header. If it's present, the server can then use this last event ID to determine which messages the client likely missed. To actually do this, the server needs to have kept a buffer or history of recently sent events, probably keyed by their IDs. Then it can look up the received ID in its history and start resending events from that point forward to catch the client up. It adds some state management complexity on the server.
And those keep alive comment lines we talked about, dot ping or whatever the server needs to actively send those to, right? To keep things open.
Definitely. Server-side applications often have their own idle timeouts, and more importantly, network intermediaries like load balancers or proxies almost certainly do. Setting those comment lines periodically, say, every 30 or 45 seconds if there's a 60-second timeout somewhere, keeps data flowing and resets those idle timers. You really need to be aware of the shortest timeout in your entire request path. The source mentioned an Azure service having a 5-minute timeout as an example. You'd need heartbeats more frequently than that.
We've circled around intermediaries being a pain point a few times. Proxies, load balancers, CDNs. How much do they really impact SSE server-side architecture and deployment?
Potentially a lot.
Mm.
They're often optimized for traditional short-lived HTTP requests and responses. Long-lived SSE streams can confuse them. The source flat out says they can inadvertently disrupt SSE streams. Buffering is a classic problem. A proxy might try to buffer the entire event stream before sending anything to the client, which completely defeats the purpose of real-time streaming.
Yikes. So you need specific configurations.
Absolutely. Careful configuration is essential. The source points out that misconfigured intermediaries are a frequent source of problems. For something like Nginx acting as a reverse proxy, you'll often need directives like proxy buffering off and proxy timeout set appropriately high. Load balancers also need their idle timeouts increased significantly.
What about scaling with multiple server instances behind a load balancer?
That's where it gets interesting. If your backend SSE servers need to maintain state about which client saw which event, or that last event ID recovery, you might need sticky sessions on the load balancer to ensure a reconnecting client hits the same server instance. But a more robust architecture, as the source calls it, is to make the backend servers stateless. Have them pull events from a shared message bus like Redis PubSub or Kafka. The event history for recovery could also live in that shared system. This way, any server instance can handle any client connection or reconnection, which makes horizontal scaling much easier.
Okay, so stateless servers with a message bus is generally the preferred pattern for scalability. And using HTTPS might help get through some proxies more reliably too.
Yeah, the source mentions using HTTPS can sometimes help in traversing proxies, likely because encrypted traffic is often less likely to be aggressively buffered or manipulated.
Okay, infrastructure configuration is clearly key. How do developers actually build the server-side logic in different languages? Are there common patterns across frameworks?
The core pattern, regardless of language, really boils down to using an event-driven asynchronous I/O model. This is the preferred model for scalable SSE servers because handling potentially thousands of long-lived connections efficiently just doesn't work well with older thread-per-connection models. You'd run out of threads or memory very quickly. So you need code that can. Accept the incoming GDT request. Send back the correct text event stream headers. Keep that underlying connection open, don't close it. Format the outgoing data correctly, data payload YAN, maybe with event.ended fields. Crucially, flush data promptly after writing each event to the response stream. You don't want the server's own output buffers delaying things. Manage that list of active client connections response streams. And handle disconnections cleanly to release resources. Optionally, implementing the last event ID recovery as that history buffer requirement.
And different frameworks provide tools for this async handling.
Exactly. In Java, Spring Web Flux with its reactive Flux Server Send event is a natural fit. Node.js, with its single-threaded event loop, is inherently well-suited, though you might manage response objects more directly. Python's ASGI frameworks like FastAPI are excellent because of Asyncio. You'd use screaming response with async generator functions. Go's built-in NephTTP and Goroutines are very efficient using the HTTP flusher interface. Rust, with frameworks like ActixWeb, also leverages async-await for high performance. The specific APIs differ. You might get a sender object in Rust or yield strings from a generator in Python, but the underlying principle is non-blocking I/O to handle many connections concurrently.
Okay, that makes sense. But how do you even know if this complex system is actually working correctly, especially when you scale it up? Debugging and observability sound tricky.
Yeah, they can be. Logging is absolutely essential. You need the log connection lifecycles, open, close, errors, maybe event transmissions, and definitely watch for reconnections and check if the last event ID header is being handled correctly. Metrics are critical for understanding scale and performance. The number of active connections is probably the most important SSE-specific metric to monitor. Also, event throughput, error rates, server CPU memory usage. For debugging, browser developer tools are your best friend on the client side. The Network tab will show you the raw event stream as it arrives. Server-side debuggers work as usual, but there's a catch noted in the sources. Many popular API development and testing tools like Postman, Insomnia, have limited or no native support for debugging SSE streams.
Really? That's surprising for a standard web technology.
It can be a bit frustrating, yeah. You often have to rely on browser tools or just use command line tools like curl, which can show the streaming response. However, for performance testing, specialized load testing tools exist that do understand long-lived connections and SSE. The source mentions Gatling as one capable of simulating many concurrent SSE clients to test your system under load.
Okay, good to know load testing tools are available. Let's touch on a couple of those advanced topics we mentioned earlier. HTTP2, we know it helps with the browser connection limit. Any other caveats or things to know?
Right, the multiplexing is the big win, getting past that old limit of 6 connections per domain. But it's important to remember that HTTP2 still suffers from TCP-level head-of-line blocking. If a single TCP packet gets lost on the network, all the multiplex streams on that single TCP connection can stall until that packet is retransmitted. HTTP2 doesn't fix that fundamental TCP issue.
Ah, interesting.
Also, just to reiterate, HTTP2 server push is still a completely separate mechanism for sending assets, not related to the SSE event stream itself. And of course, you need full HTTP2 support end-to-end client, all intermediaries and server to get the benefits.
Makes sense. What about SSE over HTTPS? Is that straightforward?
Absolutely essential for security, really. You should always use HTTPS in production. HTTPS encrypts the entire stream, providing confidentiality. It ensures the data isn't tampered with in transit integrity
Yeah.
and lets the client verify it's talking to the right server, authentication. There are no specific SSE protocol level changes needed to run over HTTPS. TLS just secures the underlying HTTP connection. It's a requirement, really.
And Core Assist, does SS interact with cross-origin resource sharing policies?
Yes, it does. Standard CORS policies apply if your JavaScript code making the event source connection is on a different domain than the SSE endpoint it's connecting to. For simple requests, the server just needs to send back the access control allow origin header, maybe with or the specific client origin. But if your client-side code sets with credentials, true on the event source, maybe to send cookies for authentication, then the server must specify the exact client origin and access control allow origin, note aloud. And it must also include access control allow credentials.
Oh.
True. The source details these rules clearly. Careful server-side CORS configuration is vital.
Okay. Compression gzip. Broadly, you mentioned SSE is text-based. Does compressing it mess up the event stream format?
Good question. No, it doesn't mess it up, and HTTP compression like gzip or Brotli is highly beneficial. Because SSE is text-based, it usually compresses very well, which means lower bandwidth usage and potentially lower latency. The source notes that Brotli generally offers better compression ratios than gzip for text, and is particularly effective for streaming data. Compression happens at the HTTP layer below the SSE framing protocol. The browser decompresses the stream before the event source parser even sees it. So using compression does not negatively impact the integrity of the SSE message content itself. The integrity relies on the SSE framing separators and potentially the ID fields.
Fantastic. So compression is safe and definitely recommended for performance. Last advanced topic, network reliability. How does SSE handle less stable networks like mobile connections or WANs?
Well, SSE has those built-in reliability features we discussed. Automatic reconnection by the browser, the server's suggested retry, delay, and the last event ID mechanism for potential recovery. That's a good start. It relies on TCP underneath, which itself has mechanisms for retransmission of lost packets. However, on networks with excessive packet loss or high latency, TCP connections can still stall or break frequently. Those keep alive's heartbeats, the comment lines, become even more essential over less reliable networks to detect disconnections more quickly or keep the connection alive through flaky intermediaries. You might need to tune the server timeouts and perhaps the client retry, value more carefully. And the server definitely needs adequate message buffering to support last event ID recovery if reconnections are common. Designing your events to be idempotent at the application level can also help handle cases where a message might accidentally get delivered twice due to a reconnect. The source also briefly mentions that the emerging HT23 standard, which runs over QIC/UDP instead of TCP, is designed to perform better on lossy networks because it eliminates HOL blocking between streams. So if SSE runs over HTTP3 in the future, that could offer further improvements for challenging network conditions.
Wow, okay. We have really covered a ton of ground on server-sent events. We went all the way from the problems with old polling techniques,
Yeah, the inefficiency of short polling, the complexity of long polling.
right up to the specifics of the text event stream protocol, the data event.fields, and that crucial client-side event source API.
And we saw how its unidirectional nature really simplifies things for that common server-to-client push scenario.
Right.
It makes it ideal for notifications, live dashboards, streaming data feeds, and how those built-in features like automatic reconnection and last event ID handling provide valuable reliability right out of the box for the client developer.
But we also definitely hit on the gotchas, didn't we? Like the old HTTP 1.1 browser connection limits, and thankfully how HTTP2 multiplexing solves that.
Yeah, and the critical need to tune intermediaries, proxies, load balancers. Getting that configuration right, especially turning off buffering off and setting timeouts is so important.
And on the server side, the importance of using asynchronous I/O models and for true scalability, architectures using shared message brokers like Redis PubSub to enable stateless servers.
Absolutely. Plus the basics. Always use HTTPS for security and leverage compression like gzip or preferably Brotli for performance without worrying about breaking the stream.
It's clear that while SSE might seem simpler than WebSockets on the surface, deploying it reliably and at scale requires a really solid understanding of HTTP, networking concepts, and server-side architecture.
It really does. It carves out a valuable niche, though. It's a specific tool for a specific but very common communication pattern on the web. efficiently pushing updates to the client over standard HTTP.
Understanding SSE gives you another powerful tool in your belt for building modern, responsive web applications.
Exactly. Knowing when it's the right choice, and importantly, knowing the architectural patterns and infrastructure considerations needed to make it work robustly in production, that's key.
So, after digging through all of this, what really stands out to you about server-sent events? Is there a key takeaway or something you'd particularly emphasize for someone considering using it? That's all the time we have for this deep dive. We really hope you enjoyed exploring the ins and outs of server-sent events with us.
Yeah, it was fun to unpack. If you want to keep diving deep into architecture topics like this, be sure to subscribe to Joy of Architecture wherever you get your podcasts.
Stay curious. We'll be back soon with another deep dive tackling another set of sources you've sent our way. See you next time.